Hello, so in this video we're going to look at solving equations using logs. And last time we did look at this already. We looked at solving equations involving logs, but we're going to look at other types of equations today. Okay, and so I guess to set us up then, well, think back, you would be familiar with, even from like Key Stage 3 or secondary school or whatever, the idea of, if we have an equation, let's say 10 equals 10, right? An equation. Let's say then you'd be familiar with the idea that you can do stuff to both sides of the equation, and if you change one part of the equation, or if you do something to one side, then you have to do the same to the other side. So for example, we could add a number, say 5, but we have to add the same number to both sides, and then we get 15 equals 15, but we're allowed to do that, right? Conversely, you could subtract 5, so we can subtract two numbers. We can also multiply both sides, let's say by 2, to get 20 equals 20, right? But the whole idea is you do the same to both sides, right? You can also divide by 2 to both sides to get 5 equals 5, right? So you'll be familiar with the idea that basically we can do stuff to both sides of the equation, right? And actually, we're going to use that concept and stretch it a little bit, because actually what we can also do is we can take exponentials, we can take logs. So what I mean by taking an exponential, firstly, what we can do is, actually, we've got this equation here, right? We can raise both equations, both sides, by the same power. Let's say then 2. So 2 to the 10 is then the same as 2 to the 10. Okay? So originally I had 10 equals 10, but now I can raise both sides by the same power, by the same base 2. Okay? Or we could have 3 to the 10 or 10 to the 10, and they'll both be the same thing, right? Both equations will be the same. 10 to the 10 is still 10 to the 10, right? So we can take powers basically of both sides. We can raise both sides by the same base, okay? We can also take logs. So again, 10 equals 10. What we can say, actually, we can also take logs of both sides. What that means is we can basically do log of any base of 10 equals log a of 10. Okay, so both sides, both numbers, I can also take logs of both sides in this way. Okay, so basically, obviously be familiar with adding, subtracting, multiplying, dividing both sides of the equation. We can also take logs and raise powers to both sides of the equation too, and that is what we're going to use to solve equations. Okay, let's have a look at this one then to illustrate what I mean. So firstly, I need to solve 3 to the x is 20. Okay, and so how I'm going to solve this, well, you can do it two ways. You could either directly convert this into log form, because we know that a log base 3, and then of 20, that equals my power x. And so at that point, I'll just put this in the calculator, right? So I put log base 3 of 20 in my calculator, and x would then be 2.7 to 7 to 3 decimal places. Okay, that's one way. However, sometimes it's very tricky to be able to just do this, right? There could be more complicated equations to just convert it into log form, or if you're a bit unsure about how to convert it into log form, what I want to start doing is taking logs of both sides. Okay, so taking logs means I'm going to log both sides. So I'm going to take log of 3 to the x is equal to log of 20. Okay, that makes sense. So I'm literally putting both sides, both numbers, as logs. Okay, now what base you pick, it doesn't matter. Obviously, they both have to be the same base to be equal, but it doesn't matter. You can pick base 2, base 5, base 1,000,000, anything. But the common one is base 10. Well, one of the common ones is base 10. Okay, and actually, it's so common that what you'll see is basically we just don't include the base. So, log base 10 of, let's say, of a number A, we literally just say log A. Okay, we don't even bother putting the base subscript because we're just lazy mathematicians. So if you see just a log with no base, right? That is 10. It's base 10. And so anyway, we'll be using base 10 just for simplicity. But okay, so with this in mind, then, so we've got the logs now. How can we solve this equation here then? Well, actually, now we're going to use the log law, right? If you remember earlier on in the chapter, we saw that any power inside the log can be brought in front of the log. So then we can say that x log 10 of 3 is log, and actually not just 10, I'm just going to say log. 10 x log 3 is a log 20. Okay. Okay, and then hopefully at this point, realise that log 3 and log 20 are just numbers, right? So actually, to get x on its own, I can just divide by log 3 to both sides. And so what I get is x is log 20 over log 3. And that you can put in your calculator. If we put that in the calculator, the log, the base is 10, right? Of 20 over log 3. I get x is 2.727. The same answer, okay? To 3 decimal places. Okay, so I will be opting with this method from here on out. I think it's a lot simple. It's quite simple to use it once you kind of understand we can take logs. Okay, okay, now we need to solve part B. And so part B, we have 5 to the power of 4x minus 1 equals 61. And you'll see now it's a bit more complicated because it's not just x. We have 4x minus 1. So the power is a bit more complicated. We need to solve for x. So what we can do is take logs both sides. So that means log of 5 to the power of 4x minus 1 is going to be log of 61. Okay, so literally put logs at both of these numbers, right? That's taking logs. And then I can simplify the equation because this is the power, right? 5 to the power of 4x minus 1 goes in front to then 4x minus 1, lots of log 5 is log 61. And so then I want x on its own, so then I divide by log 5 to get 4x minus 1 is log 61 over log 5. Okay, and then 4x then. 4x, if I add 1, it's going to be log 61 over log 5, add 1. Okay, and so therefore x is going to be a quarter, right? It's going to be all this divided by 4. So a quarter of log 61 over log 5, add 1. And so if I put that in a calculator, so I do a quarter of log base 10, right? There's a hidden base 10 if I'm not including the base in my log. Base 10 of 61 over log base 10 of 5, add the 1, I get x is 0.889 to 3 decimal places. And there we are. Okay. Okay, here I'm asked to find the solution to the equation 3 to the x is 2 to the x plus 1. Okay, and it's even more complicated now, this equation, because now actually we've got hidden powers of x in both sides of the equation, right? So it may take so kind of trying to convert it to log form directly can be even more complicated. So again, to make it easy on ourselves, we can just take logs, as it will be more straightforward, right? It'll be more apparent what to do. So if we take logs of both sides, so again I'm going to do log of 3 to the x is equal to log of 2 to the x plus 1. And now notice I have, because they're both powers, right, I can bring the powers to the front via the log law. So x log 3 is going to be equal to x plus 1 log 2. Okay, and at this point we just essentially rearrange to get x on its own to solve for x. If I expand this firstly, so x log 3 will be x log 2, add 1 log 2, that's just log 2. And so then I can move this to the other side to get x log 3, take away x log 2 is equal to log 2. And actually then I can factorise an x. What I don't want to do, I can factorise an x. So log 3 take away log 2 equals log 2. Now what I was going to say is, I could do, but I don't want to then. You might think, well, I'm subtracting 2 logs, so I can simplify even more. You can do. You can bring it as one division. You can say that's 3 over 2 as one log. But actually, we don't need to, because we just want to solve for x. As I say, we don't want to do more work than we have to do. So then to get x, spot then that x is simply log 2 divided by the log 3 minus log 2. Right? And so I can just put that in the calculator. I don't need to simplify it. So then the value of x I get is, again remembering there's a hidden base 10, okay, but when there's no base, the base is 10, okay, if I don't indicate what the base is. And I get that is 1.7, what's the round to? 4 decimal places, okay. 7095 to 4 decimal places, and there we are. Okay, so hopefully you get the idea of taking logs, right? The first step, taking logs. Okay. And what we can also do is actually think back to quadratics. We can also solve this guy's quadratics with exponentials, and then we can solve them using logs. So this is a disguised quadratic, meaning it's a quadratic. Well, it can convert to a quadratic. It's in quadratic form, but it's not an explicit. But it's not apparent, right? If I write this out, then right, I'm saying this is actually a quadratic. But it isn't a quadratic in the form ax squared and bx plus c. I need to get it into this form, and using a substitution might help. So again, we looked at this in quadratics, so if you need a reminder about how we deal with disguised quadratics, you can look at that. But here, okay. So notice that actually 5 to the 2x, notice I can split up the powers as follows. I can say that's 5 squared times x, right? Or actually 5x all squared, actually. Either way, right, that's the power law, that a to the power n multiplied by n is the powers multiplied. So I can say that 5 to the 2x is 5 to the x times 2, right? So it's 5x squared. So with that in mind, hopefully it's a lot more apparent now. This is a quadratic with 5 to the x, right? So then if I say that u is 5 to the x, then my substitution, then 5 to the x squared, that's going to be u squared, right? And then 5x is u, so minus 12 lots of u, add 20 equals 0. Now we're in the explicit quadratic form. So it is a quadratic, we've got it into one. Okay, so at that point we can solve it. So if I use the formula, that would be 12, take plus or minus the root of minus 12 squared minus 4 lots of 1 of 20 over 2 lots of 1. And so if I put that in the calculator, I get u is 10, or u is 2. So that's the solution to u. But remember, I want to solve for x. So I need to convert u back into x using what I've done here, this substitution, right? So if u is 10 or 2, then that means 5 to the x is 10 or 2. Now, how do I solve these? These are like mini equations, right? These two. How can I solve this? Well, this is where logs will come into play. So then I can take logs of both sides. To say that firstly, for this equation, 5x is 10, log 5 to the x is 10, and so I can bring the power x to the front to x log 5 is log 10. Oh no, so it should be log 10, sorry. Log 10. And so their x then is log 10 over log 5. And so that will get me, if I put that in the calculator, at 1.43 to 2 decimal places. Okay. Now, actually, you could just, I think it would probably be a bit quicker if you just convert it directly into log form. So if I solve this, if I put it into log form, log of base 5 of 2 equals the power x. So that I can just put in the calculator. But if you're not confident with that, again, I can convert it into, I can take logs instead of both sides. So log of 5 to the x is log 2 now. And so similarly then, x log 5 is log 2. So then x, I divide by log 5. So log 2 over log 5. And that will get me, if I put that in the calculator, 0.43 to 2 decimal places. And so there we are. Those are my two solutions there. Oh, 3 significant figures. Oh, my apologies. Well, that'll be 3 significant figures. This, 0.43, 0.431. Okay, I didn't. There we are. The 3 sig figs. Okay. Okay, there we are. There's my final answer. Okay, cool. So again, we can. You need to be able to spot and deal with disguised quadratics like this by recognizing what squared term you have here, and then you can solve that in the normal way, and then we can use the logs at the end. Okay, so that's really it. So let's have a look at some exercise questions. So we need to solve the following equations, giving the answer to 3 significant figures. So here, part A, we have 3 to the x plus 1 is 2000. So again, I can take logs. So log of 3 to the x plus 1 is log of 2000. So then I can bring the power x plus 1 to the front. So x plus 1 log 3 equals log 2000. And so then x plus 1, if I divide by log 3, log 2000 over log 3. And so then x then on its own, we subtract 1. And so if I put all of that in a calculator, I get x is 5.9, anything to round 3 sig figs, okay. 5.92 to 3 sig figs. Okay, then part B, we now need to solve log of 5 of x minus 3 is minus 1. Okay, so again, there are many ways we can do this. We can convert this into exponential form, or remember the trick I said last time, this minus 1 number, I can convert that as a log. So minus 1 log 5 of 5, because then that will cancel to 1. But actually what we can do is just bring this minus 1 as it's in front to as a power. So then that'd be 5 to the minus 1. What I can do instead is I can instead take exponentials to both sides. So specifically, I'm going to take powers of 5. So I have I have log 5 of x minus 3 is minus 1. What I can do is actually instead, I can raise both sides by 5. So 5 is my base to the power of log 5 of x minus 3 is 5 to the minus 1. Now why 5 in particular? Well, obviously it matches the base, but think about it. I will go over this more in the next section, in the next video, but for now, this particular equation, I've got a base. This is an exponential with a log. Well, actually, we discussed that exponentials and log are inverses, right? Which means the base, because the log is being raised by 5, right? So that means because they're the same base, they effectively cancel. So the exponential 5 cancels with the log 5. So effectively, I'll just get x minus 3 is 5 to the minus 1. That will always be true as long as you make sure you raise it by the same base, okay? If the bases are the same, then you can do this. The base will cancel the log and you're just left with what's inside. So the x minus 3 is 5 to the minus 1, because again I raised minus 1 by 5, right? So 5 to the minus 1. That's taking exponentials of both sides. Okay, so, well, 5 to the minus 1 is just a fifth. And so at that point, x is 3 add a fifth. And so then x will be, if I just work that out, 16 over 5. Or as a decimal, just 3.2. Okay, and there we are. So again, we can solve equations not only by taking logs, but by taking exponentials as well. Okay, but I'll cover more on that next time because it'll be more relevant in the next section. But yeah, we can do that alternatively. Okay, so we've got more hidden quadratic questions to practice. So we first need to solve 2 to the 2x, add 3 lots of 2x. Is minus 4 equals 0. Well, again, hopefully you spot it's a disguised quadratic, obviously because I told you, but hopefully you see that actually this 2 to the 2x I can rewrite as 2 to the x all squared, right? Add 3 lots of 2x, minus 4 equals 0, then spot that 2 to the x is the quadratic, so I can say u is 2 to the x, and so then this will transform to the quadratic. Well, 2 to the x squared is going to be u squared, right? And then 3 lots of 2 to the x is going to be 3u. Minus 4 equals 0. Okay, so I can solve it. Does it factorise? So two numbers that multiply get minus 4, add to get 3. 4 and 1. Yes, because 4 and minus 1 can be my factors, right? Because I multiply to get minus 4, add to get 3. So u plus 4, u minus 1 equals 0. So u is minus 4 or u is equal to 1. Right, and so obviously I want to solve for x, not u, so I'm going to need to bring this back in. So 2 to the x is equal to minus 4. Or 2 to the x is 1. Okay, now, hopefully you can spot the first one. We're not going to get any solutions because it's saying an exponential is negative. But remember, my exponential graph is always positive, right? It's above the x-axis. Alternatively, if you didn't spot that, if you proceeded to solve normally, if we take logs, then log of 2 to the x is log minus 4. Now that you should spot as a problem. If you were to put that in your calculator, log of minus 4, you'd get math error. So that is undefined. So log minus 4 is undefined. So there are no solutions here. So no solutions to 2 to the x is a minus 4. Okay. Now with this one, so 2 to the x is 1. You can probably spot the solution to this, but again, if we take logs, so 2 to the x is 1, then log of 2 to the x is log 1. So then x log 2 is log 1. Now log 1 is 0, right? If you put that in the calculator, or you remember either when we looked at that special rule, that anything log base anything of log 1 is always 0. But anyway, we get 0, so then x, if I divide by log 2, well, 0 over log 2 is still 0, so x is 0. And I said you could spot it because remember what this is saying here, if you just stare at it more, I guess, without trying to think too deeply, this is saying that 2 to the power of something gets me 1. Well, anything to the power of 0 gets me 1. So you can approach these questions in many ways. But there we are. Okay, part B, we now need to solve the equation 4 lots of 3 to the 2x plus 1, add 17 lots of 3x, or 3 to the x, minus 7 equals 0. Okay, so it's a bit harder to spot, I guess, what the, quadratic can become, because this 3 to the 2x minus 3 to the 2x add 1, it's quite a complicated power, right? A little tip probably is that 3 to the x here is probably going to be what my u has to be, right? But at the moment, it's not clear how this is squared. I have 3 to the 2x add 1, so how can I make that squared? So what I'm going to need to do, so what I need to do here is I kind of need to use some log laws to kind of simplify and split this up. I'll do it here. So 3 lots of 2x plus 1. Well, actually, firstly, notice I can say that's 3 to the 2x times 3 to the 1. Right? That's the power law, right? A to the m times a to the n, different powers, I add the powers. So here I'm adding the powers, so I can split it up into 2 multiplications in this way. Now actually 3 to the 1 is just 3. So that's 3 lots of 3 to the 2x. So if I bring that into here then, that'll become 4 lots of 3 lots of 3 lots of 2 to the x. Add 17 lots of 3 to the x minus 7 equals 0. Now actually I can just do 4 times 3 to get 12 lots of 3 to the 2x. Right? And again now 3 to the 2x, hopefully you can spot, I can say that's 3 to the x squared. Add 17 lots of 3 to the x minus 7 equals 0. Now hopefully you can spot I have the quadratic that in u is 3 to the x. If therefore that'll become 12 lots of 3 to the x squared, that's going to be 12u squared, and 17u minus 7 equals 0. Okay, so if I solve that then, u is going to be minus 17 plus or minus the root of 17 squared minus 4 lots of 12 or minus 7 over 2 lots of 12. And so if I do that, I get u is a third, or u is minus 7 over 4. Okay, and so then again I'm going to need to bring back in the x, so u is 3 to the x. So 3 to the x is a third, or 3 to the x is minus 7 over 4. And again, you're probably going to spot here there are going to be no solutions, because it's saying that an exponential is a negative, which cannot happen. Any exponential has to be positive. Okay. Alternatively, again, if we were going to take logs, you would have log of 3 to the x is log of minus 7 over 4. And that minus, that negative, you can't have in the log, so that would be undefined. So you would spot very quickly there'd be no solutions from there. Okay, so then we can solve this equation. So 3 to the x is a third. Again, you probably won't spot what the solution will be if you think about powers. But if we take logs, then log of 3 to the x is a log of a third. So then x log 3 is log of a third, So then simply x is going to be log of a third divided by log 3. And so if you put that in your calculator, you get -1. Okay, and that makes sense because what this is saying here is that if I put -1 in here, I get the reciprocal 3, which is a third. So that makes sense. Okay, so that's my solution, and that's really it. Okay, so x is -1 is the only solution there. Okay, cool. And so hopefully now you'll be a lot more comfortable with disguised quadratics, particularly with like exponentials. Okay. Okay, we're going to finish off with an exam question, and actually, we can deal with exponential models with logs, so we can find missing values with logs and work with logs more in more detail. So here I'm told that the value of a vintage car, so that's in pounds, which is T years after it was valued on the 1st of January 2001. So the value is modelled by V is AP to the T. Right? That's my model, so V in terms of T. And it says that the value of the car was 32,000 on the 1st of January 2005 and 50,000 on the January on 2012. And we need to find P and then show that A is this. So we need to find A and P, okay, in my model here. And I'm going to use these values here to help me. So firstly, I've got this information here. I'm told the value is 32,000. So V is 32,000. And then what's the corresponding? What time would that be? What value of T would it be? Well, I'm told the value is 32,000 on the 1st of January 2005. Okay, but the models start at 2001. So how many years have we gone from 2001 to 2005? So you got 2002, that's 1 year, 3, that's 2 years, 2004, that's 3 years, and then 2005 would be 4 years. So T would be 4. Okay? And so at that point, I could just substitute that in. So then if 32,000 for V is going to be AP to the 4. Okay? Then I've got this information as well. I'm told that V is 50,000. Right? On the 1st of January 2012. So again, how many years between 2001 initially to 2012 is 11 years. The T would be 11 at this point. Okay, hopefully that makes sense. So 50,000 is going to be AP to the 11. So actually, if I label these two equations, these are simultaneous equations, right? So 32,000 is AP to the 4, and then 50,000 is AP to the 11. So we've got two equations and two unknowns, A and P. So we can solve for A and P, but how am I going to do that? It's quite a weird simultaneous equation, right? So you could substitute, you could rearrange one equation somehow. So maybe you could rearrange the first equation to say that A is 32,000 over P to the 4, then substitute it into here. However, what you could, that's a safe way, you can do that. What you could do instead is actually, and again, this tip, this little trick, well not trick, but this strategy can come in handy with more complicated simultaneous equations you might meet later on in the course. But what you can do is actually just divide the two equations instead. So I could do the second equation divided by the first one. So then that would be, well, AP to the 11 divided by AP to the 4. Okay? And then that would be the same as 50,000 over 32,000. Right, that's a lot simpler now. Because actually the A will cancel. And also if we use our power laws, if I'm dividing with different powers, I subtract the powers. So P to the 11 minus 4 is 7. So P to the 7 is this fraction here. So 50,000 over 32,000 is 25 over 16. Okay, so then P, I'm going to need to take the 7th root, okay? So the 7th root of 25 over 16. Right, if I put that in the calculator, okay. Now, that's obviously going to be a special button because it's the 7th root. So, on the calculator, that would be, on my calculator, the class of Wiz, it's above the sign button. So, you got X with this little box. That's the key you need, that's the button you need to press. But, you need to go into shift mode because it's in yellow. So, if you'd get then, if you press that, you'd get this symbol. So, any root here, the root number, and then a big box inside. Anyway, so if you press that, and then, so if you do the 7th root of 25 over 16, again, go into shift mode, then press the button above the sign button, at least on my calculator, you'd get 1.0658 to 4 decimal places. There we are, okay. So that's the value of P. Cool. Then I need to find A. Now, so then I'm going to substitute that back in to either equation here. So let's substitute it into the first one. So let's sub P into the first one. Okay, so then 32,000 is going to be AP to the 4, right? That AP to the 4. But we know what P is. P is this 1.0658 to the 4. And so therefore A is going to be 32,000 divided by 1.0658 to the 4. And so if I put that in a calculator, I get 24,796.8022. I assume I'm going to have to round that. What does it say? It's approximately 24,800. Well, yeah, 24,000. So that's approximate to 24,800, right? If I round it to 3 significant figures, right? To 3 significant figures, because then this 7 here, the 100th, right? The 796 would have to round up to 800, and so yeah, that's great. There we are. So that's the value of P and A. P and A. Then it says, with reference to the model, interpret the value of A and P. So again, command word interpret. What that means in exams or in questions is interpret. You need to give the context of what it means. So like the real life meaning of what the value is. Okay. So in this case, we're talking about a value of a vintage car. Okay. So what does that mean in reference to that vintage car? Okay. So I'm going to restate the model then. That might help. So part B. So remember V is AP to the T. But actually instead I know that A is 24,800 roughly. P, which is 1.0658 to the T. That's my complete model, right? So firstly, it wanted the value of A, right? Now remember, with exponential models, when we looked at exponential modelling, the number in front, so I think we looked at, was it A e to the bt? It's the same sort of thing here. The number in front, the A is to deal with the initial value, right? If I was to set t to 0, then V would be 24,800, also 1.0658 to the 0. Well, actually, anything to the power of 0 is 1. So that is 24,800. So actually, the initial value of V, when t is 0, is A. Right? So A is the initial value of V. So that means the initial value of the vintage car, okay? The initial value of the vintage car. Or, so A is the initial value. Or, I guess more specifically, the value of the car initially when it's 1st of January 2001. Okay, more specifically. The value on the 1st of January 2001. So that's what it means by interpret, right? I'm giving what it means, so not just the initial value of V, but I'm interpreting it, right? I'm giving the real life meaning of what A is. So then not the initial value of V, but the initial value of the vintage car, because that's what the question's on about. Okay, so I'm applying it to the real life scenario they've given me. Okay, then it says to interpret the value of P. Right, so P is here, right? Now, remember with exponential modelling, again, if we go back up here, we said an exponential model is A to the BT. The B was to deal with the rate, it's the factor of the rate of increase. So remember, if we were to differentiate A to the BT, so if I said Y is this, and dy dx, or dt, is going to be B lots of Y, because then the B comes in front, so I multiply F it by B. So then B lots of Y, so the B, right, that is a factor of the rate of increase, the factor for the derivative. And that's the same here. Here, okay, it's the same here. So this number here, this 1.0658, is saying that that's saying that the value V is increasing by 1.0658. It's being multiplied, but so 1.0658 is the number, or the factor, for which the value of V, or the value of the vintage car, or the value of V, the value of the vintage car, is increasing by, is multiplied by, sorry, because it's a factor, right? So it's multiplied by every year. Okay, that's important. So think about it. Initially it's 24,800. Then what this is saying is that I'm multiplying 24,800. Then every year I'm multiplying by exactly 1.0658. So if I'm and so you can actually think of that then alternatively as sort of like, if you think back to GCSE when we looked at compound interest percentages, this is a multiplier of a percentage. So alternatively we could say, or the value of the car is increasing, and then if we convert this multiplier as a percentage, if we that'll be 6.58%, right? So it's increasing by 6.58% every year. So you can think of it either way, right? But yeah, that can be quite tricky. I think that's quite tricky, that is, to spot that. We did look at it, but that's what it means. But yeah. So yeah, you just need to remember that it's the factor for which it's being multiplied every year. So it's increasing by 6.58%, right? If I were to move this decimal 2 forward, because I'm multiplied by 100, because it's a percentage, right? It's 6.58% increase every year. That's what effectively what this number's doing. Okay. Okay. So part C. Okay, we got that out the way with. That's quite tricky. That was, especially for this part here, to find the value, what the value of P meant. Anyway, for part C, we now need to use the model to find the year for which the value of the car first exceeds 100,000. So what does that mean when it exceeds 100,000? That means that V has to be greater than 100,000, right? But remember, V is indeed here. V is actually 24,800 of 1.0658 to the t. So if we want the value of the car to exceed 100,000, so that means V is greater than 100,000, then the year, the value of t, is equivalent to just solving this inequality. Oh, so this has to be greater than 100,000. So we can solve this inequality, right? And actually, it looks very scary. Like, how do I solve an inequality like this? But actually, it kind of works how you expect. There's nothing too complicated here. We will use logs, but actually, it works quite nicely, as you'd expect. So firstly, well, if you want to just solve for t, we need t on its own. So it'd be best to just divide by 24,800 first. So that means 1.0658 to the t is going to be greater than 100,000 over 24,800. Does that simplify? Should do. Yes, this is equivalent to 1.0658 to the t is greater than 125 over 31. Okay. Now I can take logs. And it doesn't affect the inequality because, well, actually, let's just take logs first. So again, we could take logs. So log of 1.0658 to the t is going to be greater than log of 125 over 31. We're allowed to do that. We can also take logs in that way, and it works fine. And so then, again, we're going to use a log. We're going to use a log law to bring the t to the front, the power t to the front. So that's going to be t log of 1.0658 is greater than log of 125 over 31. Now t, then we can divide by this log here. So then t is just simply greater than log of 125 over 31 divided by log of 1.0658. Now now one little thing you need to check is, obviously, we're dividing, right? We're dividing by this log here. Log 1.06 blah blah blah. Now, because we're dividing by essentially a number, obviously with inequalities you need to pay attention if you're dividing by a negative number. Now actually this log is positive. Logs can give me a negative number, but actually if you put that in the calculator, you'd be fine. That'd be positive, so we can divide and keep the inequality where it is. Just a little thing to check. Make sure it's not negative, the log. So if it was, obviously you'd have to flip the sign, the direction of the inequality. That's all fine, and actually makes sense, because actually if we were to work that out, if we work out this whole log fraction here, that would be 21.88 blah blah blah. Now that makes sense, because obviously if you think about the question, it says to find the year when it first exceeds the value. So it makes sense for t the years, right? T has to be above this value. So that makes sense. Anyway, so that's my solution. Okay, so this is the value of t we got, is 21.88. But we shouldn't round necessarily here to the nearest integer. So let's think about what the question said. So it wants the the year when the value first exceeds 100,000. So the year means, obviously, if it's 2012 or 2005 or 2001 or 2000 or whatever, that's the year it's on about. Now let's think about it. So specifically the value of t has to be above 21.88, so it could be like 21.89 or something like that. So think about it. T is between 21 and t is 22, right? Now as a year, so t is 21 and t is 22. Now as a year, remember the model actually starts at 2001, so t is 0 there. Now think about it. When, let's say t is 21, that'd be 21 years after, so that'd be 2002. Okay, so this is year 2002 and 22, sorry. So then when t is 22, that'd be year 2023. Now, this value of t is 21.88 means the value is above 100,000 in between 2022 and 2023, okay? In between the 1st of January of 2022 and the 1st of January 2023. So, the value, obviously, it exceeds 100,000 in between these two dates. So the year it has to fall into is in the year 2022. Say like November, something like that, November 2022. But it's in the year 2022, okay? Hopefully you understand that, right? Because t is between, if it's 21.88, it's between 21 and 22. So it's between the 1st of January 2022 and the 1st of January 2023. So it has to still be in 2022 at some date. So the year is 2022. Okay? Okay, hopefully that made sense. It's quite tricky, that is. But yeah. Right? So the year when it exceeds 100,000 is in between 2022 and 2023. So it still has to be in 2022. Okay, between 1st of January 2022 and 2023. So there we are. Okay. So yeah, that is that. So that's the questions. So that is solving equations with logs. We're going to look in a bit more detail about logs again next time. But for now, that's it. I'll see you next time.